Hello, my name is Nora Harris. So today I'll be talking about the code of my dissertation topic, detection of Alzheimer's disease through magnetic resonance imaging. So here I'll be showing my Python code that I did for the topic that I chose. So first we'll be downloading the entire GitHub repository into the collab or local machine. It's cloned into a folder called adme, from which I took my dataset. The next step is importing the necessary things that we need to move forward with the code. So here we are having pandas, which we need to load CSV or tabular data, and NumPy, which is needed for numerical operations, etc. And there are machine learning libraries like label encoder, which converts class labels into numbers, and standard scaler, which standardizes tabular features. Um, for some for visualization tools, we are using TQDM as a progress bar for loops, and Matplotlib, Seaborn, etc. for plotting and visualizing. And we are using sklearn decomposition, manifold, PCA, TSNE for dimensionality reduction to show the clustering. And then for deep learning, we are using VGG16 and models like CNN. So here, this is the path given. This is the image path, and this is the CSV file path. And in this step, we are loading the images and applying pre-processing. So here, for the tabular data, that is the metadata, the missing age values are handled using FILNA, the median, and we encoded sex and group using label encoder, and scaled age with standard scaler for normalization. And for the image data, that is MRI, we loaded grayscale images and resized them, normalized pixel values to a 0 to 1 range, and converted grayscale images to RGB for compatibility with VGG16. So this dual pre-processing ensures consistency for multimodal input. And then we'll be going to feature extraction. So we are using a pre-trained VGG16 for feature extraction. So we removed the top layers and used output from block 5 bool. We extracted deep features using predict and flattened them to 1D. So here you can see the sample view of images after pre-processing. This is the feature engineering part for the tabular data. This is the descriptive statistics. This is the part where we are flattening the images to 1D, that is one dimensional. And here we are combining both images and the tabular data. So why we chose VGG16 is because it provides powerful image features even with small data sets. So my data set is comparatively smaller. It only has 421 images. So these are some of the EDA plots or visualizations that I did. This is the age distribution graph, and here we can see the sex distribution. This is the group distribution. We are having 3 classes: AD, CN, and MCI, that is Alzheimer's disease, cognitively normal, and mild cognitive impairment. This is the age by group um, box plot, and this is the patient visit type distribution count plot. This is the visit type distribution across the groups, and this is the rolling average of scans over time, that is 30 days. Here we can see the sex by group graph, and this is the correlation heat map. This is the age KDE by group plot. Now we have some pie charts. This is the sex pie chart and a violin plot which shows age by sex. Here we have a hist plot, that is a stacked age histogram by group. Here we have sex proportion by group pie charts, and another box plot which shows age by group. Here we have a pie chart showing group label and a violin plot showing group versus age. So this is the part where we do the train test split. So for preparing a machine learning compatible dataset, we already combined the image features and the tabular features using NP concatenate, and we are splitting the data into train and test sets with stratified sampling to preserve class distribution. Now the machine learning models which I did here are random forest, decision tree, XGBoost, support vector machine, and gradient boosting. So here are the results of each of the machine learning models that I did. Support vector machine was the lowest performing model, and gradient boosting was the highest performing model with 75% accuracy. The evaluation methods we used are accuracy, precision recall, and F1 score. Now we are moving on to the deep learning model. So here we are having an input branch 1 which has the CNN layers for MRI images, and 3 sets of convolutional 2D plus max pooling 2D, and they are flattened and passed through a dense layer. And the input branch 2 has tabular features such as age and sex, which we took from the CSV file, and it's passed directly into the network. And then a fusion happens where we merge both branches using concatenate, followed by dense layers and final softmax layer for 3-class classification. So a unique point here is it is a true multi-model model with dual input architecture, even though the earlier 5 machine learning models are also multi-models. So here we are training the CNN model using Adam optimizer, and we are monitoring training versus validation loss and accuracy. We are applying early stopping to avoid overfitting. So this is the CNN model accuracy. It is a bit low compared to gradient boosting. So here we are having a CNN training and validation accuracy and training and validation loss plot, and we are doing some visualizations. This is the PCA of the combined data, and this is the TSNE of the combined data. Here we are doing a score comparison of all the models which we used, that is random forest, decision tree, XGBoost, SVM, gradient boosting, and CNN. And we are also giving a model performance comparison graph here. This is a multi-class ROC curve for the CNN model alone. So this is all. The purpose of this project, or the aim, is to detect Alzheimer's disease and its early stage, especially MCI, using multimodal data, that is combining MRI images and tabular clinical data. And the approach I use here is traditional machine learning models and a custom CNN deep learning model, and we are comparing it both. So that's it. Thank you.